Hello everyone, myself Shweta Shah and I am your instructor for the subject Computer Organization and Architecture. In this subject we have started unit 7, that is the Computer Arithmetic, and in this session we are going to see today the topic that is floating point arithmetic operation. In this we are going to see the addition, subtraction and the multiplication operation. So let us start with the basic consideration for this floating point numbers. So basically floating point numbers are in form of m into r raised to e. That is, the m is the mantissa, r is the radix, or you can say base, and e is the exponent. Okay, so for any number you are representing in the floating point, then it will have three terms. That is the mantissa terms, radix terms, and the exponent terms. We will consider this basic register consideration where our data is going to be stored inside the A register and B register, and result is going to be stored inside the Q register. Here capital letters represents the mantissa terms, small letters represents the exponent terms. Okay, so here for the B register, capital B is the mantissa, small b is the exponent, capital A is the mantissa and small a is the exponent. And for this A1, that is the first bit of that particular mantissa terms, and that should be 1 for representing that particular number in the proper floating point representation. And these numbers are having, mantissa are having the signs, that is the BS and AS, that is the sign of the mantissa. And this Q register is having the Q as the mantissa part, small q as the exponent part, and qs as the sign bit. And this is the E flag that is used for storing the carries in between particular operation. And these are the parallel adders and the comparator circuits. Mantissa requires only the addition, but the exponent terms are requires also comparing whether this both exponents are equal or not for the addition or subtraction operation also. So this is having the adder as well as the comparator, while the mantissa is equals just the addition. Now let us see the addition and subtraction operation. So during the addition or subtraction operation, two floating points operands are kept inside the accumulator and the BR register, and the sum or difference is going to be stored inside the accumulator register. That Q register is going to be used for the multiplication operation. Okay, but for the addition or subtraction operation, accumulator and BR registers are enough. Now let us see this algorithm can be divided into the four subsequent parts. First part is the checks for the zero. In this we are going to check whether these numbers are zero or not. If it is already zero, then you doesn't require to do the operation of the addition or subtraction. So in checking in lastly whether your number is zero, instead of that you have to check for the first whether these numbers are zero or not. So first we will check for the zero, then we will have to align the mantissa. That means your exponents should be same. For addition or subtraction operation, your exponent should be same, then and only then you can add the mantissa. So you have to check for the exponent whether they are equal or not, and then depending upon that you have to align the mantissa. And after this aligning the mantissa, you have to do the addition or the subtraction operation, whatever you have asked. And after addition or subtraction, you have to normalize the result. Okay, so for addition or subtraction operation, you have to take care that your exponents value are same. Then and only then you can do the addition of mantissa. Okay, so now let us see this thing with the algorithm. So this is the basic algorithm that you can use for this addition operation. Here capital A, capital BR represents the mantissa terms, small a and small b represents the exponent terms, AS and BS represents the sign of the accumulator and the BR resistors. Okay, that you have to take care. Now first we have to check for the zeros. So this is the part for the check for the zero. First we will check for the BR, whether BR is 0 or not. If it is 0, then your result is in the accumulator. Okay, so if it is 0, then you have to end already because your result is already in the accumulator. If it is not 0, then you have to check for the accumulator, whether the accumulator's content is 0 or not. If it is 0, then you have to put the BR resistor into the accumulator. Okay, if it is BR is not 0 but accumulator is 0, then you have to put the BR's content into the accumulators contain a resistor, because your result is in the BR but your ultimate result is going to be stored inside the accumulator, so you have to shift that particular data into the accumulator resistor. And you have to check for the operation, whether you were asked for the accumulator plus VR resistor or the accumulator minus VR resistor. So if it is the addition, then it is okay, but if it is the subtraction, then your result is going to be negative. So you have to change the sign of the AS. Okay, so this is the basic operation for the checking for the 0. If BR is 0, then your result is already inside the accumulator. But if it is your accumulator is 0, BR is not 0, then you have to shift the BR's content into the accumulator and check for the operation. If it is the subtraction operation, then change the sign of the AS. And if it is the addition operation, then it is as it is, sign is as it is. Okay. Now, next you check for the 0, but your numbers are not 0. Then you have to do the addition or the subtraction operation. So let us see what will happen if it is not 0. So after checking for the zeros, you have to align the mantissa. That means your exponent should be same. I can add only the numbers like 10 into 2 raised to 2 plus 5 into 2 raised to 2. I can't add the numbers like 10 into 2 raised to 5 and 10 into 2 raised to 4. I have to align the exponent. Okay. So here we will check for the exponent, whether they are equal or not, by using this condition A is and B. If it is equal, then you will continue for the operation. If it is not equal, then you have to align the mantissa. If A is greater than B, then you have to shift B and increment the exponent by 1 for the B. And if it is A is less than B, then you have to increment the A and shift A right side. Okay. So whenever you will shift right side, your exponent will be incremented by 1. So you have to check for this whether A is less than B or the A is greater than B. Depending upon the requirement, you will shift the A or shift the B and increment the exponent. Okay. So if we shift this particular bit, like our number is like 0.01, and if we shift this number right side, that means number will be like 0.001. So at that time you have shifted this numbers right side, but your value should be same. So at that time you have shifted right side, but exponent should be incremented by 1, so that your value of that number remains same. Okay. And so that is the case over here. After this shifting, your mantissa is going to be aligned. Okay. Then you have to check for the operation. This is the basically same structure what we have used for the addition or subtraction. If your addition operation is there, and you have to check for the sign, whether both numbers are positive or negative. If your addition operation is there and both numbers are having the same sign, whether positive or whether negative, that means you will do the addition operation. But if your operation is of addition, but your both numbers are having the different sign, that means one is positive, another is negative. So ultimately, whether you will told to do the addition operation, but actually you are going to do the subtraction operation, because one is positive, another is negative. Okay. So you have to check for that thing. Similarly for the subtraction operation, if both of numbers are having the same sign and your operation is of subtraction, then you will do the subtraction operation. But both numbers are having the different sign and you were told to do the subtraction operation, then you will going to do the actually addition operation. Okay, that we have seen in the previous session also, and that concept we are using over here. So we have to check for the sign of the mantissa. If addition operation is there and the signs are equal, that means if you do the XORing operation, the result will be 0. So you will do the addition operation, and that result is going to be stored inside the EA resistor. The E is the flag resistor, A is the accumulator resistor. EA is equals to A plus B. But if the sign is addition operation is there and sign is not equal, that is XORing result is 1, that is 1 is 1 and another is 0, so your XORing will be 1. So at that time you will do the subtraction operation. But subtraction operation, that means you will add the 2's complement of b, that is b bar plus 1. So EA will be equals to a plus b bar plus 1. Similarly, for the subtraction operation, if sign is equal, you will do the subtraction operation. Sign is not equal, you will do the addition operation. Okay. After this addition or subtraction operation, you have to check for the E flag. Okay. First for the let us see for the addition operation. For the addition operation, if your E flag is 1, that means you have to shift this accumulator's contain right side and increment the exponent by 1. We are using this 2's complement method. So if this carry is not generated, that means E flag is not generated, that means your number is negative. If it is not generated, that means number is negative, that means you have to complement the sign and complement the number. Okay, that is done by a is equals to a bar plus 1, a is equals to as bar. Okay, so this will complement the number, 2's complement, and the sign is changed. And after that we have to check for the A1 bit, whether this A1 bit is 1 or 0. If it is 1, that means your mantissa is aligned. If it is not 1, that is 0, that means you have to shift that, but this shifting will be left side. Okay, because your number is like 0.000 something kind of, and you have to make this as a 0.1, so you have to shift left side. Okay, but we don't know how many times we require to shift it a left side, but we know that A1 should be 1, so we will shift this A left side and decrement the exponent by 1 up to when this A1 becomes 1. Okay, when A1 becomes 1, your result is generated, and that is inside the accumulator. But for the E flag, if it is Z1, that means carry is generated, and if carry is generated and if you check the accumulator's contain, if it is 0, then the contain, your result is 0, and that is going to be stored inside the accumulator. That is already stored. Okay. So this is the basic algorithm for the addition and subtraction, where you are first checking for the 0, then you are aligning the mantissa and doing the addition operation or subtraction operation, and lastly another time you are normalizing the result after the result generation. Now let us see the multiplication operation. In this multiplication operation, your multiplicand is in BR register, multiplier is in the QR register. First we will check for the 0. Any of this contain is 0, that is BR or QR is 0. Your result is going to be 0 and your data, your operation is completed. But if it is not 0, then you have to do the multiplication operation. In multiplication operation, you will multiply the mantissa and add the exponents. Okay, so here we are adding the exponent, that is a is equals to a plus b. That first we have stored q inside the accumulator mantissa, and then we will do the just addition operation, and we will subtract some bias if there is some bias is there. And this is the part for the exponent. Now for the mantissa, you will do the simple multiplication operation that we have seen in the previous session, that we will use for this mantissa terms. And then you, after multiplication, you have to check for the A1 bit, whether this A1 bit is 1 or 0. If it is 1, then your task is complete. If it is 0, then you have to do the shift left operation and decrement the exponent by 1. And then your task is completed. So here we have just checked for the zeros and add the exponent and do the multiplication of the mantissa. Your whole multiplication algorithm is there, and after the multiplication operation you have to check for the A1 bit. For the normalized operation, A1 should be 1. If it is not 1, then do the shifting operation and make it 1. Okay, so this is the basic multiplication operation for this floating point numbers. So here we are ending our today's session. If you have any query, then you can contact me.